This is lecture 3, layout planning models and design algorithms, part 1 for IE 4355 facilities planning. The course objectives first are to develop an understanding of the principles of facilities location, layout, and material handling systems, and to practice designing facilities. So in this objective is going to be part of this lecture. Learn formulations, models, and analytical procedures for the study of facilities layout planning. In this is also one of the things that we're gonna do in this lecture. Learn fundamental principles of material handling, be able to design layouts, incorporating products, process, and personal requirements. So the agenda for this lecture include the introduction, and then we're gonna talk about basic layout types, layout procedures, and algorithms approaches. The learning objectives for this lecture are to understand the interactions between layout planning models and design algorithms as they relate to facilities planning. So let's start with the introduction. The generation of layout alternatives is a critical step in the facilities planning process. The layout selected will serve to establish the physical relationship between the activities. Most facility layouts can be viewed at two levels. The block layout, which shows the location, shape, and size of each planning department, and the detail layout, which shows the exact location of all equipment, workbenches, and storage areas within each department. Our focus is primarily on quantitative methods for developing and evaluating alternative block layouts. So basic layout types. In lecture 2, we identify 4 types of planning departments: the fixed material location departments, the production line departments, the product family departments, and the process departments. Identifying the right number and types of departments that are going to be used to populate the layout is a key step that the facilities planning must perform first. So once you identify the right number and the type of departments that you are going to be using for the facility, then you can move forward in terms of locating those departments, which is what we are going to try to do now with the layout procedures. Layout procedures, different procedures have been developed to aid the facilities planner in developing layout alternatives. They can be classified in 2 main categories: construction type and improvement type. The construction type layout methods basically involve developing a new layout from scratch. So in this type of method, you're basically given a clean canvas and you can paint as you need. So you're starting from scratch, so you have the liberty to decide or move things as you wish. The improvement procedures, on the other hand, generate layout alternatives by seeking improvement in an existing layout. So those are the main 2 procedures: the construction and the improvement. So Apple's plan layout procedure, these are the steps that they follow to procure the basic data, analyze the basic data, design the productive process, plan the material flow pattern, consider general material handling plan, calculate equipment requirements, plan individual workstations, select specific material handling equipment, coordinate groups of related operations, design activity interrelationships, determine storage requirements, plan service and auxiliary activities, then determine the space requirements, allocate activities to total space, consider the building type, construct the master layout, evaluate, adjust, and check the layout with appropriate persons, obtain approval, install the layout, and follow up on implementation of the layout. Reads plan layout procedure, analyze a product or products to be produced, determine the process required to manufacture the product, prepare layout planning charts, determine the workstations, analyze storage area requirements, establish the minimum aisle width, establish office requirement, consider personal facilities and services, and survey plant services, and provide for future expansion. Risk plan layout procedure. The layout planning chart is the most important single phase of the entire layout process. It incorporates the following: the flow process, including operations, transportation, storage, and inspection, standard time for each operation, machine selection and balance, and material handling equipment. On the next slide, I'm going to show you an example of a layout planning chart. So as you can see here, we have a layout planning chart for a specific operation. And you see the summary here at the top, which summarizes the operations, which are denoted by a circle, the transport, which are denoted by an arrow, the inspection, that are denoted by a rectangle, the delays, and the storage. In this summary, you have additional information, the number and the time in terms of seconds. This is the current layout, and this is the proposed layout, and shows the difference between them here. So at the bottom, what this shows are the steps and the details of the present methods, and then they tell you the type of method that is used. So if it is manual, visual, and so on. And then for each one of the lists, you are identifying what's happening using the symbols, right? So you can have a visual perspective of what's going on in the process. So you start in storage, this transportation, so you can see how many transportation steps are in the process, how many operations, how many inspections, is there any delays, identify. And then you also have information about the distance. So when you're moving things, how far and how long it should take you. You also have the time for the operations. So how long does it take in seconds? And you can also have some information about the cost per unit if needed. This slide, actually, it's presenting or an introduction to the systematic layout planning, or SLP procedure. And systematic layout planning procedure or methodology is used often, and it was developed by Richard Muddard. The framework uses activity relationship diagrams as a foundation activity. So the systematic layout planning is very important. We're going to be using this often. It's one of those methods that are easy to use and very important, gives you very good solutions if applied correctly. And that's what we're going to discuss next. So in this slide, I have a summary on that chart, on that figure on the left, shows the steps to develop a layout using the systematic layout planning method. So at the top, you have the input data and activities, and then you use that information to determine the flow of materials and also start developing the activity relationships. So using the flow of materials and the activity relationships, you can develop the relationship diagram. And then you can integrate with the relationship diagrams, you can add information about the space requirements and the space available to develop a space relationship diagram. Using the space relationship diagram, then you can integrate any modifications or considerations or practical limitations to finally develop some alternatives. And then those alternatives can be evaluated in step 10. So based on the input data and understanding of the roles and relationship between activities, a material flow analysis or a from-to chart, which we discussed in the previous lecture. So that's flow of materials, flow analysis using the from-to chart, and an activity relationship analysis using the activity relationship chart are performed. So activity relationship, as we discussed in the previous lecture, we can use the activity relationship chart, and this allows us to determine between departments of offices, which ones are required to be close to each other using the closeness rating. And the reason behind it, we can use also coding method for that. And then looking at the information that we have in terms of activities and the discussion that we have with the people in the facility, we can start listing the type of relationship that qualitative and then the reason behind it using these activity relationship charts. And then using that information and the flow of materials, we can start developing what is known as a relationship diagram, which is an example is illustrated in figure 4. The relationship diagram position activities spatially. Proximities are used to reflect the relationship between pairs of activities. So in this type of diagram, you see that there's the nodes are representing the departments. So in this case, we have 9 from 1 to 9, and then we have different type of lines. So each line represents strength of the connection between those departments. Like in the same way that we define, for example, A, E, I, O, U, and X, those letters represent a closeness need, right? The same way we can show that using different type of lines. So you see you have the dotted line, you have another type of dotted line here, then you have the bold line and so on. So those have a meaning. So for example, these bold lines might represent that the connection between those two departments are absolutely necessary. you as the designer you are in charge of determining the type of line that you want to use and what it will represent. On the next slides, I'm going to show you some examples how that can be done. So for instance, there's a line code here associated with the values of the letters of the relationship diagram. So as we discussed, this is the meaning of the letters, and then we can have a line code associated with it that we can use in this relationship diagram. Okay, so instead of using dotted lines and bold lines and so on, this coding here is using multiple, like 4 lines to determine absolutely necessary 3 lines. If it is especially important, 2 lines. If it is important, 1 line. If it's ordinary, unimportant, there's no line. And then undesirable, then we have this line. And then we also have numerical weights associated to it. So using that line code method, then we can start connecting the departments. And those lines will help us in moving the departments around to see if we have a limited area. Let's say we have something like this, and we want to fit all these 5 departments inside that box. Then knowing and seeing these lines will tell us, okay, we can move around these departments, but we need to make sure that, for instance, 2 and 5 stay close to each other. So I'm going to move them here. I want to make sure that 2 and 5 stay together, right? And I can play with the other ones. In this case, it looks like 5 and 3 must be far away, and 5 and 4 must be far away. So something like this might be a possibility. 3 and 4. So that's the idea. You have the arrows representing the strength of the connections or the limitations of the locations of these departments, and you want to use that when you are moving these departments around to fit a specified area. So the number of lines here represent paths required to be taken in transactions between the departments. The more lines, the more interaction between the departments. So the relationship diagram positions activity spatially. Proximities are typically used to reflect the relationship between the pairs of activities. So in this diagram, it looks like all departments have the same size, which is not typical. But again, if we want to fit, let's say we have this kind of a box shape here, but let's say the area of that we have for the layout is something like this, then we have to move these boxes around to try to fit this area in by taking into consideration the strengths of the connections given by the lines. So here's a better picture of the same. Now we have the actual area of the departments. So again, that's really important. We have the area, we have the strength of the connections. So now we want to start moving these boxes around to fit the given area and see what will give us the best performance. So the space relationship diagram involves the determination of the amount of space to be assigned to each activity. So that's where we start showing the space in that relationship diagram. And then based on modifying considerations and practical limitations, a number of layout alternatives are developed and evaluated. So you see here, using this information, we can start finding ways to place those departments around. And then we're going to use an evaluation of flow between and distance to see which one is going to give us the best performance. The preferred alternative is then identify and recommended. Okay, so that's what, again, a very important method, the systematic layout planning procedure. So very important for the class, and very important for what you're going to be doing in your project. So we will use this through the semester. So there's also other algorithms approaches. The layout procedures presented in the previous section provide a framework to construct or improve a layout, but they do not provide formal procedure or algorithm for some of the critical steps associated with layout design and evaluation. The models and algorithms we present in this section provide us with objective criteria to facilitate the evaluation of various layout alternatives that emerge in the process. Most layout algorithms can be classified according to the type of input data they requires. It could be qualitative flow data, such as a relationship chart. It could be quantitative flow data, such as the flows or flow matrix expressed as a from-to chart. And some algorithms accept both relationship chart and from-to chart. Layout algorithms can be also classified according to their objective function. For example, minimizing the sum of flow time distances. So flow time distances, meaning that you want to minimize the sum or the summation of how far you have to travel to perform all the movement in your department, let's say for a day. So you take into account the flow from department I to department J, and also you take into account the cost of moving a unit load one distance from department I to the department J. So there's a cost, there's a distance associated, and then you are going to multiply flow, the distance, and the cost of moving that unit. The summation of all those movements for all departments is what's going to define your objective function. And you want to minimize that cost. And then we have maximizing an adjacency score. In this one, basically you're trying to put together or locate together those departments that have a higher volume of flow. So you are going to quantify the flow from department I to department J, and then you want to make sure that the adjacent of department I and J, so you're placing that department as close as possible, so your flow is maximized. Other algorithms approaches: graph-based method, CRAF, MCRAFs, MIP, logic multiple. So there are multiple algorithm approaches. The one in red are the ones that we are going to cover in this class. Graph-based method, CRAF, the MCRAF, and the MIP, which is mixed integer programming. So the graph-based method is the first one. The graph-based method is a construction type layout algorithm, and it uses the adjacency-based objective. The graph-based method considerations, the adjacency score does not account for distance, nor does it account for relationships other than those between adjacent departments. Dimensional specifications of departments are not considered, the length of common boundaries between adjacent departments are also not considered. The arcs do not intersect. This property of graph is called planarity, and the score is very sensitive to the assignment of numerical weights in the relationship chart. So let's look at the graph-based method. So as an example, consider a company that wants to develop layout for its new 5 departments of equal size. And we have the relationship chart here illustrating the weight. So the higher the value, the higher the importance of these departments being connected to each other. So we can draw a relationship diagram based on this information. We can draw that using departments as nodes. So I have 1, 2, 3, 4, and let's put 5 here. And then I can start linking those as a network. So from 1 to 2, this is 9. From 1 to 3, this is 8. From 1 to 4 is 10. From 1 to 5 is 0. And then from 2 to 3 is 12. And from 2 to 4 is 13. And from 2 to 5 is 7. From 3 to 4 is 20. And from 3 to 5 is 0. And then from 4 to 5 is 2. So that's the relationship diagram. So for the graph-based method, the procedure is the following. Step 1, from the relationship chart, select a department pair with the largest weight. So in this case, the department with the largest weight is department pair with the largest weight is our departments 3 and 4 because the relationship is 20. So those are selected to enter the graph. In step 2, we select the third department to enter. The third department is selected based on the sum of the weights with respect to departments 3 and 4. So what we are going to do is when we're going to start this chart or this graph, which connects 3 and 4, because those are the departments with the highest weight. And that weight is 20. So we are going to start adding more into this graph. And you'll see how this is going to allow us to decide the location of the departments. We start with 3 and 4, and now we want to decide who's going to enter next. So step 2, I'm going to list 3 and 4 here at the top, because those are the departments that are already in in the graph, and then I had to decide who's going to enter next. And my options are 1, 2, and 5. Those are the departments that are still missing. So now I'm going to look at the relationship between 1 and 3, 1 and 4. So from 1 to 3, the weight is 8. And from 1 to 4, the weight is 10. And then from 2 to 3, the weight is 12. And from 2 to 4, the weight is 13. From 5 to 3, the weight is 0. And from 5 to 2, the weight, from 5 to 4, the weight is 2. So now I'm going to add the total to see which one has a largest weight when we consider the relationship between 3 and 4, or with 3 and 4. So this is 18, this is 25, and this is 2. So this one is the best, it's the highest. So what I'm going to do now, I have this graph already. You know that these two are connected, the weight is 20. So now I'm going to add this new node to the network, which is 2. And the reason I'm adding 2 is because it gives you the best performance when compared to 3 and 4. Okay, so that's the next. So department 2 is chosen with a value of 25. Step 3, pick the 4 department to enter by evaluating the value of adding one of the unassigned departments represented by a node on the face of the graph. So now we're gonna consider those departments that are not yet in the graph, and we are gonna evaluate them against the departments that were already selected. So the relationship between 1 and 2 is 9, 1 and 3 is 8, and 1 and 4 is 10, for a total of 27. And between 5 and 2 is 7, 5 and 3 is 0, and 5 and 4 is 2, for a total of 9. So we're going to add 1 now to this network. So remember, this was 20, and this was 12 and 13, with 3, 4, and 2. So now let me do this a little bigger. I'm going to redo this because I need more space here. Actually, let me use the original colors also. So we started with red. We have 3 and 4 and 20 here. Then we added the node 2. So node 2 was added, and then we added these 2 arcs with 12 and 13. And now I'm adding another one, which is node 1, because it has the highest value. And then I'm going to locate that one here in the middle. So here we connect that to 2, right? So this is 9, this is 8, and this is 10. Okay, so department 1 is chosen with a value of 27. Okay, so we have one more department that we have to integrate, but we need to choose where we're going to place that node. Like right now, we have 3 options. We have this area, we have this area, and we have this area. So now I have to identify on these 3 areas, which one is the one that gives me the best performance. So that's what I'm going to do next. So determine on which phase to insert the last department. So I have 5, I have 1, 2, 3, and 4. And this is 0, this is 7, this is 0, and this is 2. Okay, so I know this is the last department, right? I know this is the last one that is gonna enter. But now I have to decide in which phase I'm going to enter this last node. So I'm going to do a little evaluation here. I'm gonna call this phases. I have 1, 2, and 3. That phase that includes those 3 nodes. I have 1, 2, I'm sorry, 1 here, 2, and 4. I have 1, 3, and 4. And I have 2, 3, and 4. Well, 2, 3, and 4 is the whole thing. So I have these 3 phases, right? 1, 1, 2, 3. I have 1, 3, 4. And I have 1, 2, 4. So this triangle, this triangle, this triangle, and this triangle. So those are the 3. And I'm gonna evaluate those 3 to decide which one is gonna give me the best performance. So if I look at 1, 2, 3 in this graph, 1, 2, 3, the total is 7. 1, 2, 4, the total is 9. And 1, 3, 4, the total is 1, 3, 4, the total is 2. So the phase that gives me the best performance is this phase, 1, 2, 4. So if I go back to my previous figure, which I have this, this, and this. This is 1, this is 3 and 4, and this is 2. And I have this, 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 and this. What I'm saying is that I'm going to enter this last node 5 in this phase 1, 2, 4. So the phase 1, 2, 4 is this phase right here. Okay, so 5 is going to be located here, and it's going to be connected here, here, here. And this is 0, this is 7, and this is 2. This is 13, this is 12, This is 9, this is 8, and this is 10 and 20. So once we have this information, we can move to the next step, which is construct a corresponding block layout um, based on the location of the nodes. So if we know the areas, we can identify the shape, which is not necessarily what's an information that is provided. But the important thing about this algorithm is that we can show the location of the departments based on the construction that we did using the addition of the nodes in the network. So if you have the area of the departments, then you can plan for the layout using the area, and then you're going to base the location of those departments based on this association of the graph, meaning that 2 and 1 has to be close to each other, 2 has to be close to 2, 1, and 4, and so on. So in this case, you see 5 is in between 1, 2, 1, 2, and 4. So if you go here, 5 is in between 1, 2, and 4. So the department is close to 2, 1, and 4. So in this lecture, or to conclude this lecture, we discuss activity relationship and space requirements. And we also discuss a couple of algorithms that are used to construct facility layouts.